Okay, so the different types of prostaglandins are there, and family or groups different. This is group one. PGE forms group one, then group two. Different types. PGA, group three, group four, etc. So different groups are there, and the first group to be identified was PGE, followed by PGF, and was first isolated again in semen, and that's why they are named as prostaglandins. And why we have differentiated different prostaglandins based on the type of the ring system. We have told that the icosanoids are commonly having a chain isoprenoid rings, isoprenoid side chain, which is starting from C1 to C20. In the case of prostanoids, they share common features like presence of cyclopentane ring system. Then in the case of prostaglandins, they are having a cyclopentane ring system. And in case of again prostaglandins, another feature is that there is a double bond on the 13th position, which is present on the trans form. And another feature of prostaglandins, all the prostaglandins are there. They are having a hydroxyl group on the 15th position. Right, these are the common features. Now the one prostaglandin will be different from the other based on the type of the double bonds present, or there will be some sort of derivatives or substituent, or the side chain will be attached to them, or there will be the absence or presence of any other additional group. So the presence or absence of certain bonds or certain substituent groups makes the different types of prostaglandins. Okay, so the different abbreviations, the different letters stands for the different types of ring system. It is in the ring system, or the structure of PGA is entirely different from that of PGB, unless the other common features are present in all throughout the prostaglandins, like the presence of 20 carbon atoms, the presence of cyclopentane ring system, and the presence of the position of the double bond on the 13th carbon atom, and again the 15th hydroxyl group are all there. But other than that, there are certain other modifications present in each different types of prostaglandins, right? And these are the different types: PGE1, E2, E3, and then PGD2, PGE2, PGF2, and PG12 and thromboxane are widely distributed in the body. There are these are written in the notes. Okay, yeah, this is the common structure of this is the PGA family. So PGA family will be having a double bond on the C10th position. That is, this is our cyclopentane ring system. So the cyclopentane ring system is having some set of changes that makes them differ from that of the other. Each group differ from the other in the difference is lying on the cyclopentane ring system. So in case of PGA, the modification is that it is having a double bond on the 10th carbon atom, and there is a presence of a keto group on the 9th carbon atom. Right, this is a C8, 9, 10, 11, and 12. So in case of PGA family, there is a double bond on the 10th carbon atom, or in between 10 and 11, and there is a keto group on the 9th carbon atom. In case of PGB, it's different. The double bond, the position of the double bond is now changed, shifted from the 10th carbon atom to the 12th carbon atom, or it is in between the 12th and the 8th position. The remaining structures remain the same. That is C1 to C8 വരെ same ആണ്, C12 തൊട്ട് C20 വരെയും same ആണ്. C13 ഒരു double bond is there. It is not shown here, but there is a double bond, and there is a hydroxyl group on the 15th carbon atom also. Right. Other than that, the modifications on each type of prostaglandins is that in PGA family there is a double bond on the 10th position and a keto group on the 9th position. In case of PGB family, the double bond is there in the cyclopentane ring system, but it is shifted from the 10th position to the 12th position, but the keto group is remaining the same. Now in case of PGC family, it's not that common, right? It is a double bond is 10 to the 11th position, so it is on the 11th position, and the keto group is remaining the same. In case of PGD, see, the double bond is moving from the 10th towards the 11th, and it is forming a keto group there, and the keto on the 9th position is replaced with a hydroxyl group. So that's the difference between PGA and PGD. Okay, so PGA family, the keto group was in the 9th position. In case of PGD family, it is shifted from the 9th to the 11th. right? So this double bond is coming from the 10th to the 11th. 11th carbon atom, it is forming a hydroxyl group here. Sorry, keto group here, and the keto group on the 9th carbon atom is replaced with a hydroxyl group. So this is a common feature of all the PGD family members. And PGE, in the case of PGE also, this, see the difference. In PGD, OH was on the 9th, keto on the 11th. In case of PGE, it is exactly reversed. The 9th keto group is remaining there while this double bond is removed. PGA now it's no E double bond is removed and is replaced with an OH group, right? And PGA compare it, you have to study that, then it will be easy for you. In case of PGF, the keto group is replaced with OH and this OH is remaining there, right? So these are the different types of prostaglandins, and PGG and PGH, it is from the PGG and PGH the other compounds are synthesized. So it's common. You don't have to study the individual structure, but you should know the common structure, general structure of a prostanoic acid. So since all these compounds are having the same structures, they are collectively known as prostanoids. And this is a prostanoic acid. This compound is known as a prostanoic acid. Prostanoic acid is not having any double bond or an hydroxyl group, but it is having the cyclopentane ring system and also the C20. So this is a parent compound, prostanoic acid. Prostanoic acid is acted upon by different types of enzymes, giving rise to prostanoids. So prostanoids will be having a double bond on the 13th position and then the hydroxyl on the 15th position, right? So this that forms the general structure of prostaglandins. Now each prostaglandin differ from each other in the position of the substituent groups and also the position of the double bond. Okay. See, this is the structure of a prostacyclin. An attachment of oxygen between C6 and C9 and forming another 5-carbon ring. The structure need not be studied, but you should know the structure of prostanoic acid. And another structure is, another compound coming under prostanoids is the thromboxanes. So, as the name indicates, where are the thromboxanes found? The thromboxanes are found within the thrombocytes, right? And they are having a structure similar to that of prostanoic acid or prostanoids. But see, there is a double bond between C1, 2, 3, 4, 5. Between the C5 and C6. Okay. And there is a double bond C12, 5, 6, 7, 8, C 9, 10, 11, 12, 13. So it's a cyclohexane ring system, right? And 14. This is a double bond. And 15th position, they are having an OH group. So this is the structure of thromboxane. Thromboxanes are of different types. TXA2, TXA3 are there. TXA family, TXB family, etc. there. So they are having individual functions also. So the most common thromboxane found in the body is a TXA2. They will be having an additional oxygen atom attached to the 9th carbon atom and 11th of the ring system. So you need not have to go into detail of the structure. You just study what I have given in the notes, right? So thromboxanes are compounds or prostanoids which are found in the thrombocytes, and they're having a structure similar to that of prostaglandins. And the most common thromboxanes are thromboxane A2 and thromboxane B2. What's the function of thromboxane A2? Thromboxane brings about vasoconstriction and platelet aggregation. We know that thrombocytes, what does the thrombocytes do? Thrombin formation. So prothrombin to thrombin. So what is happening there? Platelet aggregation, right? So vasoconstriction and platelet aggregation, thereby forming clots. And this particular action is inhibited by aspirin, right? While TXB2, there is a stable degradation product of TXA2. The product is TXB2, and they are synthesized during hepatotoxicity, right? So acute hepatotoxicity induced by acetaminophen. It's a drug given during liver diseases, and during these conditions, thromboxane B2 is largely synthesized. So they are highly active metabolites of PGG2 and prostaglandin N2 peroxides. What are PGG2? I'll come to teach you when we enter into the synthetic pathway. So they are synthesized from the prostanoids itself of prostanoic acid, and it is synthesized. The different types of thromboxanes are synthesized by an enzyme known as thromboxane A synthase, and they are present in the endoplasmic reticulum of the lungs and platelets and carries out the conversion of PGH2 to thromboxane A2. And the thromboxane A2 is having a very short half-life. We have already studied that prostanoids are having, or eicosanoids are having, a very short half-life. It's less than 1 minute, after which the molecule will be channeled for degradation, and they brings about the formation of thromboxane B2, which is inactive in nature. Right? So this is a chart or flow chart of synthesis of eicosanoids. So from where does eicosanoids synthesized? The eicosanoids are synthesized from the polyunsaturated fatty acids, omega-3 or omega-6, and we'll first learn about arachidonic acid. So DAG or phospholipids. The first enzyme to come into action or synthesis of eicosanoids starts with the action of phospholipase A2 and in case of DAG, it is a phospholipase C. In case of phospholipids, it is a phospholipase A2. Right? So, membrane phospholipids or diacylglycerol undergoes lipolysis by phospholipase C or phospholipase A2. That depends on the substrate. If the substrate molecule is diacylglycerol, then the enzyme is phospholipase C. But if the membrane phospholipid is undergoing degradation, like phospholipid, membrane phospholipid is undergoing lipolysis, then the enzyme is phospholipase A2. So the enzyme synthesis starts with phospholipase A2 or phospholipase C, cleaving the molecule to release arachidonic acid. Arachidonic acid will be released out from the structure of phospholipid or diacylglycerol. We know that diacylglycerol is glycerol having two fatty acids attached to it, and the fatty acid will be arachidonic acid. So once phospholipase C acts on DAG, what happens? Phospholipase C acts on the diacylglycerol molecule, converting it into monoacylglycerol and free arachidonic acid. So this is how the eicosanoid synthesis is initiated. So once the arachidonic acid is released, what happens? It is removed. What happens to it? This arachidonic acid will be acted upon by the enzyme. The pathway is known as cyclooxygenase pathway. We are going to study the synthesis of prostanoids. So if it is a cyclooxygenase pathway, then the synthesis will be prostanoid synthesis happening. So prostanoids includes prostaglandins, cyclins, and thromboxanes. So cyclooxygenase pathway involves a very much important enzyme known as PGH synthase, prostaglandin H synthase. It is also known as PGHS. So PGHs are of two different types, PGH1 and PGH2. There are two isoforms of this enzyme, PGH1 and PGH2. So this is PGH2. That's why it is indicated as PGH2 synthase. So PGH2 synthase or PGH1 synthase. There are two different isoforms of PGH synthase, PGH1 and PGH2 synthase. So in case of prostanoid synthesis, usually it is a PGHS2 that is coming into action. So PGHS2 acts on arachidonic acid, resulting in the formation of prostaglandin H2 or PGH2. Again, it's a multi-enzyme complex. PGH synthase, prostaglandin H synthase is a multi-enzyme complex having two enzyme activities. One is the COX, that is cyclooxygenase activity, and the other one is a peroxidase activity. So there are two enzyme activities present on the PGH synthase enzyme, and this PGH synthase enzyme carries out cyclooxygenase activity and also the peroxidase activity. Again, cyclooxygenase, then different types are there, COX1 and COX2, right? So COX1 and COX2, and this is forming the rate limiting step, that this phospholipase A2, DAG, the phospholipase C or phospholipase A2 forms the rate limiting enzyme of the pathway. So whether the synthesis has to be taken out or not, it is synthesized, it is decided by the regulatory enzyme or the rate limiting enzyme, phospholipase C in case of DAG and phospholipase A2 in case of phospholipids, right? So this enzyme, these two enzymes decide whether the pathway has to be continued, and if the consent is obtained. If the pathway is getting continued, what happens? Arachidonic acid will be then acted upon by the multi-enzyme complex PGH synthase.